This is binary. It's a bunch of ones and zeros, but computers are able to process this data as information like numbers, words, and everything you see on screen. So how are computers able to do this? Let's look at this lamp. There's two possible outcomes. Either this light could be off and there's nothing. This is basically just the same as zero. Or it could be on, meaning we got something. We got electricity. So that equals a 1. Right, and that's really what it is. It's just flipping a switch on and off. Oops. Just flipping a switch on and off. That's where you get the 1 and 0. Alright, let's look at an example. Here we got the word hello. Pretty much the word every quarter starts off with. And in binary, it looks like this. Now you may have noticed that they're in chunks. They're separated by spaces. A single bit by itself is not that useful. Here we group them in 8. This is called a byte. Right, 8 bits equal a byte. Here we got 5 bytes representing 5 letters. But not only does it get us the word hello, but these bits can actually represent numbers. But where am I pulling all this from? Well, let's take a step away from binary for a second and look at something familiar. Here is the number 123, but we can actually simplify this into 1 times 100 because it's in the hundredths place, 2 times 10 because it's in the tenth place, and 3 times 1 because it's in a ones place. But even this we could simplify. So instead of being 3 times 1, it could be 3 times 10 to the power of 0. This is known as base 10, where the base is 10, the power is 0 because that's the starting position. We start at 0. And then we got 3 as the value. Right, and the same thing with 2. 2 times 10 to the power of 1. The value is 2, the base is 10, and the positioning is 1. Because we start from 0. It's the same thing in binary, or base 2, where the base is 2, you got the positioning, and we got the value, which is either 1 or 0. So when we have 1 bit, it's the same as 1 or 0 times 2 to the power of 0, or 1 times 1. Then in the second bit, it's worth 2 now, because 2 to the power of 1 is 2. Right, you can also think of it as doubling each value as you add a bit. Adding up all 8 bits would give you 255, a total of 256 values, or 2 to the power of 8. But how are we able to represent words and letters? Well, it turns out to actually get numbers from binary, we gotta assign these letters to unique binary digits. Realistically, A could be 1. Like, it doesn't really matter as long as other people know the system, right? And that's where ASCII comes in. It assigns every letter, number, and symbol a unique binary code. For example, the letter H is assigned this binary digit, or the number 72.